questions from the homework, my children? Now is your chance to ask. Because I know all of you did the homework. Every one of you. 8B? Yes. Were there any before number 8? I hear crickets chirping. Maybe everyone's doing the homework. Maybe they're learning. They've learned that if they do the homework, the test marks go up. Nod your head. Yes, nod your head. Yeah, see? There we go. 8B. So, you found the electric force from part A? Okay. I'm going to make a little argument here. See if you can see where I'm going, Sally. Electric force is equal to K Q1 Q2 over R squared. True? Oh, didn't want to erase all that. Try again, Mr. Dueck. Isn't that actually electric field, KQ over R squared? So if they want me to find the electric field, it's going to be the force at that location divided by the charge at that location if I get electric field by itself. That was our second definition of electric field. We said you could find electric field two ways. You could go KQ over R squared, find each charge as electric field, and then add them vectorially. If they're both to the right, add them up. If one's right and one's left, bigger minus smaller. But I think since I found the force and I know the charge at that location, I think I can go 0.895 divided by the charge 1.5 times 10 to the negative 6. I think, try that, but I think that should give me my 4.61 times 10 to the 7th newtons per coulomb. It does not. Am I incorrect here? Oh, at point X. I'm sorry. Read the question, Mr. Dueck. Have I mentioned I have a cold? If not, I'm going to use that as my excuse right now. Okay? I'm drugged up. That's going to be on the internet. Yeah, I know. Let me try that again. They want the electric field at point X. Sally, here's what I'm going to do. I'm going to cover up both of these. Find the electric field with a radius of this distance, with that point there. And what direction? To the right, because the positive would want to move away. Then I'm going to cover up this one and this one. Find the electric field from here with this distance. And I'll be using, for each of those, E equals KQ over R squared. What direction? This one to the left, because it would want to go to the negative charge. Then I'm going to cover up these two and find the third one. I won't give you one with 3 charges. This is overkill, but if you handle it, that should get you there. Does that make sense? Oh, and this one would be to the right. So you have to the right plus to the right minus to the left. Is that okay? I'm not going to give you 3. 2 charges, absolutely. So something like... I thought there was one on it. Well, in the previous homework, I gave you 2 charges. Any others? Okay. So we've looked at electric force, Stephen. We've looked at electric field. We've looked at electric potential energy. What we're going to look at today is voltage. Lesson 5. So a little bit of review. Good way to go out into spring break. And remember, I said to you, these were typed, and Regan, since you're new, this was actually a friend of mine typed this up as a workbook. It's great, but he typed it in Word 95 for Mac, and it's starting to show its age. So that there is supposed to be micro coulombs. You're going to see that more and more as the diagrams get older. A totally great question on a test or on a quiz. Find the electric field, magnitude and direction, 75 centimeters east of a 2 microcoulomb charge. So here's my field point location, and we would like to find the electric field. Electric field is equal to, what is the equation to calculate electric field? KQ over R squared. And remember, K was 9 times 10 to the ninth, one of the easiest constants out there to memorize, even though you don't need to. It's on your formula sheet. I'll get you a formula sheet and stuff later on. Actually, I should probably get you one now. Or over spring break, just watch my lessons. You'll be fine. Q, what's the charge? Oh, 2 microcoulombs. What was micro again? Whenever we saw micro, what did that tell us to write? 10 to the negative 6, worth memorizing because otherwise you're looking it up all the time. All over this distance in meters, so 0.75 squared. What's the electric field at that location? Can you crunch the numbers, please? And remember we said most electric fields are, thank you, Ryan, for pulling the headphones off totally. I appreciate it. I was going to say something and I thought, no, I'll let him notice. Most electric fields are in the thousands or tens of thousands or even hundreds of thousands. So 32,000 units. Coulombs is charge. This is not charge. Remember what the units for electric field were? And I'll give you a hint. If you forget, I think you can sort of figure it out on your formula sheet, because does your formula sheet not also have that electric field is F over Q, doesn't it? Although I think it has a big Q. Doesn't it have that? Yeah? Ah! Coulomb. Direction. Which way would a positive right there want to move if it could? To the right. Or east, or well, to the right. Because they said, oh no, they said east. I'm sorry. They used east in the question. I'll try and be consistent with what they use in the question. B. Says, find the force on a 1 Coulomb charge placed at that point. So if I want to find the force, put your pencils down and look up. I could do this. I could. Not gonna, but I could. Where that is 9 times 10 to the ninth. Q1 is 2 times 10 to the negative 6. Q2 is 1 Coulomb, huge charge, divided by R squared. There is a shortcut, though. Because I know the electric field, I can go straight to this. I can say, if I know the charge at that location, I know the electric field at that location, I should be able to find the force at that location. How do I get letter F by itself? So we're going to say this. The force at that location is, and I usually use a lowercase q times E. Why do I use a lowercase q? I'm kind of thinking that this is the big planet and this is the tiny satellite. I'm trying to always relate it to gravity. In this case, lowercase q is 1 whole Coulomb times E, which is 32,000. Don't you dare reach for your calculator. What is 1 times 32,000, Connor? I knew even you could get that. Excellent. 32,000 units, Connor. What did we just find? Huh? Newtons. What direction would the force be? I think to the east if this was a positive charge, but they didn't say include direction, so I'm good. What would the force be on a 1 millicoulomb charge? Well, I would put 1 times 10 to the negative 3 there. What would the force be on a 2 millicoulomb charge? It would be 2 times 10 to the negative 3. But a shortcut, if you know the electric field at that location, then if you know the charge on any point you put there, you can find the force very quickly, which actually makes sense to me anyways, because, Sally, E is KQ over R squared. This is actually KQ Q2 over R squared. It is the Coulomb's law in disguise. So I'm not going to worry about C and D. We would crunch the numbers. what I want to do is get into the concept here. Electric field tells us how many newtons of force per Coulomb at that location. For energy, there is an analogous, a similar concept. It tells us how many joules of energy per Coulomb at that location. How many joules will any Coulomb at that location possess? How much energy per Coulomb is there at that location? This quantity is commonly called potential, and unfortunately students get the word potential mixed up with potential energy, and it's not your fault, it's a bad term, but it's also called voltage, and I'm going to use the term voltage more often than not because voltage doesn't confuse me with potential energy. Voltage is different from potential energy. Potential doesn't sound very different from potential energy because potential's the same root word, same first word. And it's given the symbol capital V. The units of potential or voltage are joules per Coulomb, sort of like newtons per Coulomb for electric field, which is the definition of a volt. And we must be careful not to confuse potential with potential energy. It's probably the most common mistake in this whole unit. And the problem is this, folks. If I say to you, question number 7, find the potential, and you find the potential energy, even though your work is all right and good, I got to give you 0 because you found totally the wrong concept. I can't even give you part marks. There's a solution to that. Keep up with the homework. What is the equation for voltage? Well, I told you it was defined as energy per Coulomb. It's energy per charge. That's the overall definition of voltage. Now let's look at what the equation for voltage would be for a point charge. It says, fill in the proof to find the potential or voltage due to a point charge Q. So here's our big planet, and we're sitting right here. If we want to move a tiny test charge, little q, how tiny? So tiny that it doesn't have an electric field of its own. Justin, Jordan, you guys with me, or I'm going to walk back there and take whatever you're looking at? You guys with me? Yeah? Because you look like you were really engrossed in something there. You sure? If it was something electronic that shouldn't have been there, put it away completely, my friends. Or I'll make you cry in love. What we're going to do here, Jordan, is we're going to move a little test charge, little q, to the field point. From here to here. And then we're going to find the ratio of potential energy per charge. So potential energy is K, big Q, little q, over R. Voltage is energy per Coulomb. It's going to be K, big Q, little q, over R, divided by Q. Let me make sure you guys are with me. So Sally, that's potential energy, and that's little q. You know what happens to this q and this q? They cancel. Really? All right, you generation that sucks at fractions. Who's in my Math 12 class? Look up. Is this a fraction? How dare I not write that as a fraction, because I'd rather have 4 levels than 3 levels. How do I divide by a fraction? Yeah, this is actually K, big Q, little q over R, times 1 over Q. You multiply by the reciprocal, and Brandon just started smiling. He got an early adrenaline rush. Yeah, it turns out the Q's do cancel. Right, Brendan? I said Brandon. Brendan? You know what the voltage equation for a point charge is? It's K Q over R. That's potential. And once you've written that down, put your pens down for a second. Connor, here is where kids find this tough. That's potential. That's potential energy. Oh, except on the formula sheet, they use that letter with a little tiny p there. Do those look kind of similar? That's electric field. They use an E there as well as an E there, but a V there. Do those look kind of similar? This is force. They look a lot alike. I know. How can you keep them straight? Do the homework. So, those are our other formulas. You don't need to write them down. Here is voltage. The voltage at any location is equal to K times the charge at that location divided by, sorry, let me say that again. The voltage at any location is equal to K times the big planetary charge divided by how far away we are from the planet. It's sort of like height, kind of, sort of. Example 3. Turn the page. You may notice that example 3 is almost identical to example 1, except all that I've done is I've replaced the word electric field with potential, and I've replaced the word force with potential energy. So it says, find the potential, or the voltage, 75 centimeters east of a 2 microcoulomb charge. Potential is Q over R. It's 9 times 10 to the 9th, 2 times 10 to the negative 6, all over 0.75. Sorry? 24,000 volts? Is that right, folks? Yeah. 24,000 volts. By the way, let's go back a half page here to this. Because voltage is how much energy per coulomb, it's a scalar. And you know what the fact that it's a scalar means? That when I calculate the voltage, I'm going to include the signs. If I have a negative charge, I'll have a negative voltage. If I have a positive charge, I'll have a positive voltage. So I'm going to put in brackets here, scalar. We're going to include pluses and minuses here. Vectors, forces, and fields, no signs. Scalars, energy and voltage, signs. So we've got the voltage. I didn't need to worry about it here because, Sally, the charge they gave me was positive. I got a positive answer. I'm more interested in B. Find the potential energy. Well, voltage is defined as the potential energy per coulomb at that location. That means that potential energy is going to be QV. It's going to be 1 times 24,000. Evan, what is 1 times 24,000? I knew you could. Joules. Why didn't you use the 2 times 10 to the negative 6, Mr. Dueck? This little q is the charge at that location. What you want to imagine is that's the charge sitting right there. The planetary charge, there. A little tiny satellite, there. I'm not going to worry about C and D. It would be the same idea. If I wanted to find the potential energy on a 1 millicoulomb charge, I'd put a 1 times 10 to the negative 3 right there. If I wanted to find the potential energy on a 2 millicoulomb charge, I put a 2 times 10 to the negative 3 right there. If we know the change in voltage, what's change in anything? It's also called the potential difference, final minus initial, between 2 points. Then we can find the work required to move a charge between these 2 points. Huh? Example 4. By the way, what's that little symbol right there supposed to be? Microcoulombs. What's that little symbol right there supposed to be? Microcoulombs. Live with it. Okay. It says, find the potential, the voltage, at location X. How many charges are there in this question? 2. So they're sending out, there's going to be 2 voltages. The total potential is going to be, add them up. What we're going to do to find the potential at X is it's going to be, I'm going to call this charge 1, and I'll call this charge 2. I'm going to find the voltage from charge 1, which is going to be KQ1 over R1. Which is going to be 9 times 10 to the 9th. 2.5 times 10 to the negative 6. All over. How far apart are we between this charge and location X? 0.2 meters. What's the voltage if this charge didn't exist? What's the voltage at location X from this charge? What do you got? Don't rush your calculators at once or anything. 113,000? Even? Let's use that because it's not my final answer. Trust me. 112,500? Scalar, so no direction. What's the voltage from charge 2? Well, does charge 2 have the same magnitude? Yeah. Same distance? So I'm just going to write the voltage at location X is going to be 2 times 112,500. That's why I said don't round off. That's the total voltage. If there was 3 charges, I'd add all 3 of them up. What do you get? And that's the 3 sig figs, so we're good. Here's what we're saying then. If you put a positive charge right there, which way would it want to move if it could? Up. So if we want to move it to location Y, we're going to have to do some work. Oh, but once we get to about here, we're going to be getting repelled. This isn't like a standard change in potential plus change in kinetic question, because I'm going to be having to do work, but once I'm past them, they're going to start pushing me away. I can use voltage. Works much better. Works much cleaner. The voltage right there, we're saying that any charge there has 225,000 volts, 225,000 joules per Coulomb of energy. Then we're going to find the voltage at location Y. At location Y, the voltage from charge 1 is going to be KQ1 over R1, 9 times 10 to the 9th, 2.5 times 10 to the negative 6, all over. What's my new radius? 0.35. What do you get? Is that right? You know what the voltage from charge 2 at that location is going to be? Same answer. What's the total voltage at location Y? It's going to be 2 times 64,285. What do you get? $128.57, 128.570, and I'll go to 3 sig figs here. 1.29 times 10 to the 1, 2, 3, 4, 5 to the 5th volts. By the way, if you're confused and going, what's the point of this? Don't worry. I'm seeing a lot of, I'm not, It's going to click in a couple of days. Volts is really a weird abstract concept. We're going to spend a couple of days on this. Right now, I'm just showing you the actual math and explaining the concepts for the first time. You'll wrap your brain around it and suddenly, oh, I figured it out, but it'll be a day or two. Tyler, what does part C want us to find? By the way, what this really is change in voltage. What's change in anything? What's my initial location according to part D? Where are we moving from? Y, final. Sorry, final is X, initial is Y. So there's final minus initial. So we're going to go 225,000. You know what? Whoop, don't want to do that, Mr. Dueck. 225,000 minus answer. And I get a potential difference of 96,430 volts. What does D want us to find? Now, up till now, I've said to you, work is change in potential, don't write this down, plus change in kinetic. Here, with more than one point, here we're moving not in nice 90-degree angles. Who cares? Energy and voltage are scalars. In fact, I wouldn't care if the question moved from point Y and did this to get to X, or if it went straight, or if it zigzagged. Doesn't matter. Energy and voltage are scalars, which is why they're so nice. We're going to use our definition of voltage. We said this. Voltage was equal to energy per Coulomb. So if I want to find how much work, how much potential energy, QV. What voltage did we move through? 96,430 volts is what we're traveling through. What charge are we moving? I've scrolled down. 1.25 milli, 10 to the negative 3, I believe. This is going to be 1.25 times 10 to the negative 3 times, I'm running out of room here. Hey, let's be clever, Mr. Dueck. Hey, cool. Times 96,430. That's how much energy it would require to move a charge from there to there. And because it's a function of energy, this is why batteries don't have joules on them. What units are batteries measured in? Volts. Volts. It's going to be very important when we do circuits. Let's see. I'm going to go this number times 1.25 times 10 to the negative 3. And I get 121 joules of work. It's as much work as we had to write to get this question, just about. I know. It's a tricky one. It's voltage. So it says this. If the charges begin and end at rest, then the work will just be the change in potential energy, which is the charge, times the change in voltage. I need to read that again, and I need to move the cough candy over in my mouth. It's about tripped on it. If the charges begin and end at rest, then the work will be the change in potential, which is the charge times the change in voltage. And it says, prove it. Work is change in potential plus change in kinetic. True? If we start and end at rest. True? Okay. Now, over here I'm going to say, for what it's worth, voltage is defined as energy per Coulomb. So we defined it. And I think what that means is the change in voltage is defined as the change in energy per Coulomb. Is that okay, Mitch? I think that means the change in potential is equal to Q change in voltage. When we're moving charges around, if you want to know how much work, assuming you're starting and ending at rest, the amount of work is equal to QV. Is this one on your formula sheet? Not directly. Is this one on your formula sheet? So this one leads to that one. Summary. Voltage can be found using the definition if we're told the potential energy of a test charge that is placed at that point. In other words, if you know how much potential energy and you know how big your tiny test charge is, you can calculate the voltage. That's the definition of voltage, joules per Coulomb. It can be calculated if we're told the planet and how far away we are from the planet. That tells us what the voltage is at that location. Further out you go, the smaller the voltage, the smaller amount of energy per Coulomb you have. We can get the potential energy of a charge system using the potential energy equation if we know the two charges and their separation. Potential energy equals K Q1 Q2 over R. That was last day. Or the definition of potential, not energy, potential, voltage, if the charge is a test charge at a known voltage point. In other words, and if I want to, work is equal to change in potential, change in voltage, plus change in kinetic. If potential energy is QV, change in potential is Q change in V. Now this seems very confusing, and with point charges it is and it's not useful. Where it's going to get very useful is we're going to take some of this and apply it to parallel plates and circuits, and for those they'll tell us the voltage. So now to find work and energy, it's a simple something times something instead of mucking around with this big thing. It's going to be nicer. Note, potential energy and potential voltage are net vectors and have no direction. So if we have several charges, we just add the joules or the watts. What's your homework? Boy, I don't think that lesson went all that clearly. I don't feel like I nailed that one, but I'll throw you to the wolves and see how it goes. Number 1. Number 2. Number 4. Number 5. What's that symbol in number 5 in the diagram right next to -2? I'm pretty sure it's supposed to be microcoulombs. It's been smooshed. Number 7. You might have to ask me about number 7. We'll see how clever we can be. Going back here. I think number 9. Okay. Gives you some questions to try. What we're going to ask ourselves when we come back is, how many of you ever got a shock before? Okay. Does the shock occur when you touch an object, or does the shock occur a split second before you touch the object? It's actually a split second before. It's when you generate a spark. It's when you get very close to the charged object, those charges have enough potential energy to jump the gap. Really, that's a function of voltage. It's how much energy per charge. What we're going to ask ourselves next class is, how much voltage do we need to get a shock? Or, more interesting, for lightning to occur. What's going on when the clouds have enough charge so that suddenly there's enough voltage, enough energy per Coulomb for them to jump the gap? Okay.